Thank you for introduction. I hope that I'm loud enough. I'm usually a loudspeaker, so I think either way it should work. So like mentioned, I actually worked on vision before, and one of the things I focus a lot in my PhD is actually like video understanding, and it has become a little bit boring in the end of my PhD on video stuff because it's all video action recognition, and then I got to think more about how is video going to be useful, and that actually leads to kind of motivate me to do robotics because I think I see a lot of human doing things in videos. I think that would be a good source of demonstrations. So learning from videos actually my motivations to come into robotics. Aside of that, but a little bit, this is my house. It has been better. This is actually around 1 year ago when my daughter is 2. She's not picking up things, but now she's better. But essentially, this is kind of a source of motivation for me to do research. That this theme motivates me to shoot a demo on this one. Basically, we have this B1 robot plus a Z1 arm that we are doing some pick and place in here. So I call this toy example because really A is picking up some toys, B is not really that realistic yet, right? So the real scene is much more complex. So my daughter is watching Peppa Pig there. So at that age is still very attractive to television. Well, now it's but less. So when we are shooting these demos, what I feel like having this robot at home, my feeling is actually the robot is a little bit too large. Even for a house in California, it's still too large to walk into. So I also give talk in New York City, and obviously that's impossible to put that robot there. So you want to, what do you want to do? So you can buy a larger house, which is actually, it was a good investment. I think as the interest going down now is maybe sooner, it's also good to buy a new house. But it's not very scalable. So that's kind of motivated me a bit on this, working on humanoid robots. So essentially, you can try to screen your robot, make it smaller, and then you can work in a narrow space. I use this figure video pictures to just show you that the humanoid can be kind of slim. And then every time, if you think about, talk about whether we should do humanoid, there's always discussions on whether I should do wheelbase or whether I should use legs as a mobile manipulator. So my thinking is basically, so bipedal walking is actually a space that is almost towards working. And from all the experiments we have been doing, I do see that is in the good time to work on, is a good place to do research, is going to be useful. And then I would foresee after 1 year, no one will be questioning whether you should use wheels or legs. I think it will work. On the second, for the practical perspective, we recently got the robot from the Harry, one of the postdocs worked with Jiajun. So he has a startup now making these wheel-based robots with arms. It's called Galaxy AI. So we bought the wheel-based robot, and it's surprisingly huge. The base is so very large. So it's not smaller than the quarterback we have. So that made me feel like, yeah, it's actually, if you want to do wheelbase and you need to make it balanced, and then you actually do a lot of things and then maintain balance, you need to have a large base. So on the other hand, you have a leg, so that can actually be more agile and adjust balance easier. So all these things make me feel, convincing me more and more to work on legs. So I'm also a purely believer in data-driven approach. So a lot of things I do is like on this humanoid space, I'm only relying on data-driven approach. So there is a lot of discussions. Basically, you should use simulation, sim to real, or you should collect real-world data, or you should study from human data, and all these different ways to acquire data to do the training. So here is my thinking process. I would like to go for it, and then And then that leads to what I believe will be the right way to how to use this data. So I actually, in the past 3-4 years, I worked on a lot of simulation and sim to real. So one of the projects that we did is actually point cloud RL. So you train point cloud reinforcement learning in sim, and then the point cloud representation transfer quite well into real, and then you do some door opening. And then we have worked on last year also combining sim and real data, that you do teleop in sim and real, you combine the data to do things. So the thing I observe from simulation is that you kind of need to make the task simple, the environment simple, so you can align sim and real so that sim can transfer to real. So I have been struggling on this a lot because like all people are doing very cool demo. When I do sim to real, I can only do this kind of, yeah, it's okay, it's doing something, but nobody cares kind of manipulation. So I think I have been struggling a lot in simulation. Real transfer, it always makes the task simple. So now then comes to the real robot. So we have very cool people here doing very cool things. So when this demo out, everyone knows about it, and then like, oh, this is so cool, and so and this and that. So that made me curious about the teleoperation space as well. So we did a few works in that direction. Why it is very cool, on the process, we do realize that it's very expensive to collect this real data, apparently, right? So it's a multi-million-dollar business now. So real data is good, but expensive, and sim data is not expensive, but it's very hard to do like complex tasks. So that is the reality we are facing. So when we try to think about what will be the next step, so some work we have done before is trying to look into human video. You are supposed to have very rich context, human doing many things in different places. You have rich context, and then you're supposed to can get a lot of complex manipulation and real data from, if you can learn from human. But that is just also a very ideal picture, right? So when we try to apply vision, do 3D pose estimation in videos, it doesn't really work very well. So we publish a paper, but yeah, it's okay, it's doing some 3D pose estimation, is providing some demonstration, but it's not really that scaling up because vision is not quite working. But what happens is recently that we do see a lot of cool VR glasses and AR devices that somehow provides quite good estimations on 3D domain. So this is an example of the hot 3D data set from the Aria glass. It is getting quite accurate 3D, but at the same time, you see the white dots in here is actually using motion capture. So it's not quite there yet, but it gets reasonable good 3D annotations to give you the data. So I think it's reasonable to explore this idea, this domain now. We have better vision or better ground truth on human data. But what strikes me, what is the turning point for me is really, is before this summer, we have this word called spatial region GPT. That's what makes me feel that I should invest in this domain a little bit more, is that we can now actually, if you're interested, you can check out the paper, but now we basically enable the vision language model to do very detailed measurement reasoning. So you ask the question that whether you can ride a motorcycle with 36-inch wide going through these two caps, and then the model is able to reason that, oh, there's actually how much distance between them, so your bicycle can go through it. So this work actually kind of give me a feeling that because it's not just about measuring, it's not just estimating, it's also about reasoning the metrics you measure. So because it's how wide it is, so you can go through this. So you can use the knowledge of spatial to do something, spatial relation to do something. So that makes me feel that can we actually use these models? Because once you have understanding on distance and reasoning on the distance, so can you actually use it to predict action? So that makes feel that it's doable. I mean, there's already a lot of VLA models before this, and you predict robot doing this and that, but you are always training on a specific scale of human robot data. You're not sure whether it's actually fitting to the data or it's actually doing spatial reasoning. But from this work, I start thinking, I become more convinced that we can use VLM to do spatial reasoning, and not just semantic level, but very detailed distance and measuring level. So that kind of leads to what it's a pretty long thinking process, but that kind of leads to the framework I'm recently more interested in. Is basically, can we train a vision language model, action model on human data? So you can predict how to plan, where the human goes, and then how to manipulate things in human action space. So it can be mid-level action, so you cannot be just very semantics. So it needs to be like some detailed description on trajectory level. And then on the low-level side, you can use teleoperation or sim-to-real to basically figure out the exact context and navigation. So all these things are actually kind of, in some sense, is modeling human. We try to modeling how human plans, training VL8, and then from low-level perspective, we do teleoperations for manipulations, and also sim-to-real for whole body control by imitating human. So there are different levels of modeling human, but I think I now believe more in this two-layer structure, like kind of model. So I will go through a different aspect of this model that hopefully in the end I can convince you this is a plausible way. So first I will first go from bottom to top. So maybe getting you to know more about low level is more convincing, as this is, in the end of the day, this is a robotics seminar. It's not just vision language. So we have this open television work that basically is just a teleoperation system, but I think the cool thing in here is really about the vision part. So we have a very cute design on the head. So this is a Unity H1 robot, but we designed a new leg that you basically move as your head in the VR glass move. And also, it basically streams what the robot see in this ZAC mini camera, in this stereo camera, streaming the vision in real time to your VR glass. So this is what the VR glass is seeing. So the student sees, who is Xixin, sees what the robot sees. And then basically you can do quite real-time teleop control. So you are streaming vision to your VR glass, and then your VR glass estimate hand pose, and hand pose do retargeting to control the robot hand to do things with relatively small latency, quite real time to do all these things. And the streaming is very useful in the sense that one aspect, so this is another example, we show that the teleoperator can actually operate the robot remotely. So this guy, Ge, who is in job market, so he is operating the robot from MIT to control the robot in San Diego. So you stream your vision across the country, and then you stream back your pose across the country to control the robot. So you can do very, very remote control by doing this vision-based thing. So these kinds of things, so we basically collect some data and then train policy. But this paper has not focusing too much on the imitation learning part. It's really overfitting. We are collecting data for this particular container, a particular can. It's not generalizing, just a disclaimer. But the cool thing is that it's actually continuously doing things. So it's robust in the particular case, and then you can keep doing the things. It's not just one time, but a little bit long horizon, keep doing the same thing. And I like this a lot from the egocentric perspective, because A is an active camera, so the policy actually predicts not only the arms and hands, but also predicts the head, how the head moves. So it's an active vision. And also this is makes you think a lot relate to all this egocentric video I used to work on. So this is pretty much how Ego 4D and how Epic Kitchen video looks like, but instead of human hand, it is robot hands. So I like that aspect a lot, and then I want to connect it to later of the talk. But this is the part I really like, the active moving camera and the manipulation with the active camera. And we can folding but but just on a particular tower again, but keep folding. And we can do folding, and then we can, so this is teleop results. So people ask how much the Inspire hand can work, right? So it's not really that good at hands, but then you still can do reasonably dexterous tasks with this egocentric vision. So we have developed in parallel 2 other teleoperation platforms, and they asked people there to try to do this task. They're actually not able to do it because when in the other platforms, when we are doing teleoperation, we are actually seeing it in the third-person view. And then this task is only doable when you have this first-person egocentric view to conduct this task. So the egocentric visual feedback is quite important to conduct much more dexterous tasks. So one is remote as control, the other is this more like dexterous task that is conducting. And then I show this one because it's so when you do 60 pose estimation, everyone do a drill 60 pose estimation, but no one actually uses it. So we figure maybe we use it to do something. So this is drilling the wood. And then to just show you how much precision you can reach. So this is also a little bit more precise control. It's not doing the exact right thing, right? Because you're not supposed to touch. But that's the extreme we can do for this. So this is a teleop thing. So in a short conclusion is basically egocentric vision is good for dexterous task and then also remote control. So we enable this. And now we basically think, can we act the robot on the whole body control on it? So this leads to an extension of the current projects that we basically also add the sim-to-real walking skills into it. So now the humanoid robot can walk and then also manipulate objects. So this work is a little bit of engineer work, I would say, because it's not exactly whole body control. We do separate upper body and lower body control. The upper body is going to use IK and retargeting to do teleop. The lower body is using reinforcement learning to basically control the walking policy. So a new technique thing in here, which I'm not going to cover, is basically how do you do robust walking as you are moving upper body a bit. So we are doing some conditional, some conditional variable for the RL. You train a VAE to encode upper body motion and then get an embedding out of it and then use it as a condition for your walking policy. So that allows us to do robust walking while we are moving the upper body. So it's a temporal solution because the UHH1 does not really have a lot degree of freedom. It's really hard to do very agile motion really. So the temporal solution we have is actually do some separations. That's we have robust walking and then also upper body control. So here just show you some teleop results again. So it's just an extension, but basically there's one guy is controlling the upper body to do things. Then there's another guy using a joystick to control the walking part. So this is pushing a wheelchair. So showing that he has some capability. And then this is basically, again, doing some walking, just pulling the cart. So doing something. So it's the exact same thing, but now we have a walking thing in here. So I think we can see the operator later for this example. So this is in our cafeteria. And then you basically walk to there. So again, it's all teleop. It's not automate. So you can put the things, go there, and then you grasp the things. So the camera is still active vision. You see that the camera is actually moving. So the guy sitting there is not doing anything useful, but the guy hiding in here is basically the guy who is doing the teleop. So he's wearing the Vision Pro, and you can see his hand motion is aligned with the kind of the robot motions. And then there's another guy that is not appearing in the video that is using a joystick to control the directions of where the robot moves. So that's sort of an idea or extensions of what we have at this point. And there's a lot of demonstrations. Are there any questions? I saw, yeah, yes.
Watching the robot, right? That it must be teleop.
Yeah. Okay.
Somehow.
I think there is some hesitation.
Every now and then it kind of goes, you know, which if it was a learned thing, it wouldn't bother you. Yeah.
Right. Yeah. But you do feel, I mean, it would be nice to have this kind of behavior to learn. So this is actually showing we can do standing as well. So it takes us a long time to train the standing thing. But anyway, so this is doing some teleop. So I think there's still, because we have remote control, so we show remote control. So a little bit acting here, but this is some a little bit acting, not very serious. We can go faster, but we are worried about the hardware, so we didn't go faster. We have faster videos, but yeah. So it's kind of robust standing as well, because this guy also went to Michigan. At that point, I was saying maybe we can do it from Michigan as well. So robust standing and then some teleop remote. That's the thing. So this control is still, so we are still exploring different UIs. So this is a lot of UI. So basically you have a UMI, like IMU, sorry. Overfitting to the IMU on the chair, and then basically you can rotate, and then your wrist can move as well. So we are still exploring different interfaces, how to control the robot. So how do you, so the interface is something we're exploring. So this work is, earlier time we have this work that is actually the same kind of controller, but we have an older version of the robot. The leg is more slim. And then we do whole body control to imitate the human motion. So I'm just showing that we can actually walk around the city. So I think the big plus of this work is we actually walk around the city. It's not in the lab. And I think this is also, because I'm giving a talk, so I show you the left part. If you see it online, it's only this part. But so yes.
Can you explain a little bit more about the vocab system? Is it like purely vision-based?
Yeah. So the input is really just there's no. So in here there's no vision. So this is really just input a reference motion. There's no mocap in here. So our input only have a reference motion and proprioceptions. So there's no observation in here, in this particular case. Yes, but teleop is the same of the open television. You basically have the visions with the Z camera, Z mini cameras on top, and then you basically see what the robots see. So that's the same. So, but this is, again, is only teleop. So the low-level locomotion does not have vision. So locomotion does not have vision. Upper body teleop has visual feedback. Yes?
What is your intuition for why egocentric camera view really helps with those more fine-grained tasks?
I think you kind of need to see it, basically, because when you are seeing the third-person view as the robot teleoperating, I mean, there's a lot of occlusion happening. For example, I mean, you don't need see the little ear plug, and then you don't see how the small box, how to articulate object, how it can unfold and collapse. So that is actually very hard. Maybe there's some occlusion and also not very intuitive, because I want to operate things in this way, but I see things in this way, and then I need to operate in this way. So that's actually not very intuitive for the human operator to do it, because you are not operating in your normal way to operate. You are seeing other view to operate, and you kind of internally you need to do the transformation in yourself to do it. Maybe if you train yourself enough, that can be done, but evocentric will offer you the most intuitive. You feel like you are inside the robot to do this thing.
Would you say that it's kind of making up for the lack of haptic feedback, or the fact that your hand is
Right.
different than a robot? Like sometimes
Haptic feedback is definitely useful. So we did actually do some study on that as well. For example, there's work I didn't show in here, where we try to do this haptic feedback as well. So you can have tactile sensor in the finger, and then you have haptics, some motors on your fingers, and then when you do teleop, you can have haptics feedback. So that is helpful, of course. It makes it much faster. But again, even with that, we still cannot do the picking up the small things. Yes. Okay.
So you said that it was able to do it like decently well, but then it was still like touching the side and it shouldn't. Do you think it's like a limitation of the hardware?
Yeah, I think the fingers is very limited thing you can do. It's really 1 degree of freedom in here. So it's very constrained. It's like a larger gripper or more robust gripper at this point. So I think, yeah, there's a lot of constraint on the hardware here.
Do you think it's still worth scaling up this data even though it's like not as good? Like, do you think it'll still be useful once you like get to a better robot?
Yes, but that will relate to what approach you are going to use to learn the representation. I fundamentally think it's possible to scale up across embodiments, but in a reasonable representation space, which I will introduce a bit later. But let me finish the first part. So I want to talk about, I kind of showed you this video a little bit because I want to go to the next thing that we recently do, that we don't separate upper body and lower body control for whole body control. Now we have a better, like a smaller robot that basically, it's just easier, makes our lives easier once you have small robots that we actually can track whole body. So you input a reference motion and then you can do the whole body tracking on this smaller robot. So we call it X42 because the previous is called X40. And so you can do motions like this. Is it playing? Okay. It makes sense to have some. So what happens is you have the human motion there, and then you try to input that motion, a retargeting version of that motion, and then that is the simulation policy, and that transfer the real. So it's actually quite aligned that the sim-to-real gap is not that huge with this smaller robot. So you have more degree of freedom, and then it's just lighter, make it easier. You can see the sim-to-real motion is quite aligned here. 1.4 meters. So this, yeah. We have studied a lot of things in here. I think one thing is still, even though it's better hardware, there's still limitations that you cannot jump too high, you cannot run too fast, you cannot do too crazy motions. So there's these limitations. So I will talk a little bit about the data set part. But essentially, the framework we are using is we actually spend a lot of time. We want to do motion imitations. We spend a lot of time to filter, to study what kind of motions data set we can use. So the answer is, it turns out you cannot be too dirty or you cannot be too small. So we talk about some data set perspective. How do we curate better data and then do human data set and then robot motion data set? But the general framework falls into a teacher-student policy. Basically, you train a policy. Again, the input is your kinematics motion, and then your policy is trying to track output the joint action to try to track the input motion, so you get robot can do the same motion. So you have some privileged information, so the joint velocity, which is very important. If you ever, there's a Disney paper that do all very agile whole body control as well. In there, they actually have a mocap system that capture the linear velocity of each joint to as input for the whole body controller. So that was very important, but we try to make it more realistic, so we throw it away. And then in teachers' policy, student policy, we just try to distill the teacher and student, and then have partial observation in the sense that we only observe the proprioceptions, and basically reference motion and limited partial observations. And then we do all this whole body control. So that leads to one important aspect is that we spend a lot of time on what is a good data set for this task. So again, we want the policy to track all the motions that as an input instead of training overfitting one particular motion. So first, obviously, it's easy to have the data set that basically does not move that much, just walking, normal walking in different way. And then we create a little bit data set. So it's all from CMU mocap, by the way. We're just manually selecting things out or in. So we eventually find the data set that is good for us. It's basically you have a lot diverse upper body motion, and then the walking is still relatively stable, not too crazy. So this is something we didn't train on at this point, but maybe we should eventually. But we only get the robot for 1 month, by the way. So we didn't train on too much crazy motions at this point. So this is the right combinations of data we have been using at this point. And so I kind of call different data set. D50 means like a small, simple motion. D250 is like have a little bit more diverse upper body motion, but stable walking. And then D500 is a lot different motions, and then the whole CMU mocap data set. And then there's basically some comparison, basically saying that if you do train on D50 and then you evaluate on D50 in distribution, obviously, then you have the best performance. And then if you train on D250 and then you evaluate on the whole CMU data set, so actually larger data set make you generalize better to the whole CMU data set. And then you try to evaluate on another data set that is not CMU mocap data set. You find you still have the 250 that the middle-sized data works best. And then other more not as clean data set actually does not generalize as well as the middle-sized data set. Yes?
Yeah. So is this data filtering kind of hardware robot things? So if I change a different humanoid,
I don't know. It's actually more manual. It's like student feels like this is feels like this is easy. So it's not currently too much code selection or something. It's like feeling. Like it's all very much manual at this point. We are trying to have some automate process like using your policy to filter, right? So we tried that, but we initially want to include that as part of technique in our paper as well, but some students just figure out a way to filter better data sets. So, yes.
Includes invisible trajectories.
Right.
So it's invisible for the robots or it's invisible for the human as well?
It's invisible in this, so it's more invisible for the robot. So it's like, what I mean invisible is like this, more exaggerating, jumping and this kind of things that is probably very hard to, I mean, this is motion more like a kinematics one. So it's hard to actually make it work in simulation. So motions like this. So I call it not visible. All right. So some results. There's another technique I want to cover. So there's a difference thing in here. So there's paper like previous paper on whole body control actually doing global key point tracking. Meaning that you have an input motion, the key points, and then you want your output key point, output humanoid joint exactly matching the absolute positions of your input human joint. And that, if not matching, give you a reward or something to train it. So that results in actually it drifts away as the policy roll out. So what we do a little bit different is like we are basically separated, like we are matching the velocity of the root velocity, and then for the other joint, we are basically it's like a relative. So you all centralize your human pose and the robot key points into the same coordinates, which is 0 coordinate in the root space, and then you do relative positions between the human joint and the robot joints. So a little bit design difference for the loss. So a lot small engineering things. These are the two things. So we are able to do some, for example, style walking. So this is like not just walking, but have a little bit style. And then it can walk outdoor. So this is just a little bit motions. We are trying more. So this is not very large motion, but you can see in the middle is the simulation results. On the right is the on the real deployment. So it's relatively aligned here. And then a little bit more. So this is doing that. Yeah. So right. And then I think this is this. Right. This is puncturing. And then a little bit more. So you actually use this degree of freedom a little bit. So it's nice to use the here. Right. Where is this? I don't know. So we start to do a lot of testing, stress testing actually. So this is a small experiment we tested yesterday that we can have the G1 robot stand for 2 hours straight without overheating, and then also with 66% battery consumption. That's important because when we are doing H1 robot, sometimes students forgot that it's standing. After 10 minutes, it just fall down because overheating. So the large robot seems to overheat quite fast, and then the smaller one is you can work for longer hours. So we're just stressing testing on this one. So that's basically the thing. So any questions? I should go to the next part. But all right. So all these things are low level, and then I'll now talk about the mid level VLA I try to do. So we first try to apply this in navigation. There's a manipulation version, but this is my home again. So my home is always the test bed for all the robots in our lab. And then so this is trying to say, walk out of the rooms and then go to my office. So this is actually the office I have at home. So this is more like vision language navigation. So some NVIDIA people in here because we are training vision language action model. So the cool thing about this work is that it defaults into the two-level framework I was mentioning. So you're training a vision language model, action model, VLA model, but you're not directly predicting the low-level control output. You're actually predicting the control in the form of language. You say basically you move forward 75 centimeters. So it's not that high level and not that low level, right? So it's not just move forward. It's actually pointing out how much you need to move forward and how much angles you want to turn. So we find this training is actually helps the model not overfitting to the navigation task itself, because we actually do co-training with other QA pairs when we're doing vision language model training. And then you have a low-level policy that basically follow the instructions. So it's separately training a low-level policy. So the benefit of this is first, you can run these things in 2 frequencies. So VLA runs in 1 hertz, and then the low-level can run in much higher frequencies. So you don't worry about that VLA is low. And then you can basically have put in different platforms with the single VLA. So we are doing the G1 now. And then I like this part a lot because the VLA now is not just training for with the robot data. It can be trained with human videos, and then you can be trained with just general question answering tasks that have general knowledge. So it's actually, we are using the VLA model, which is the NVIDIA VLM model. And then we are co-training not only the robot data, but also the VLA data at the same time. So it's not forgetting about all this vision language model data. So we are also co-training with these videos as well. So the video is basically, we construct, this is the real estate 10K videos. If some of you have worked in vision, you know this is the real synthesis data set. And then you have a camera walking around the room. So basically, we find some way to label the caption for it. Now we can basically have these captions like this is walk down the hallway to enter the bathroom. So this is walk up the stairs and stop at the top. So we use some VLM to label it, and then use it back to train our vision language model. So it's turning how many degrees, moving forward how many centimeters, and this sort of thing. So this is enabling, having representation like this, enabling you use this general video to train as well. It's not just the habitat videos. So basically, this is rolling out the policy. It stopped a little bit because the way it works is actually you send an image to the robot, and then you're going through your phone. The phone sent to the server, and then you compute the text in here, and then you send back to the robot. So it's a little bit not on board entirely, but at the low level is on board. Yes.
Quick question: the phone here is basically used as a Wi-Fi hub.
Yeah. So we didn't manage to run VLA on Orin on board chip. It's still very slow, even though we are actually working with Song's group on all this quantization and all these things. Still far away. So this is again my house. So this is showing that lag robot is useful because there are questions on lag robot is not so useful. So we are able to working out my windows. Yes.
So the instruction is always like in metric space, like move forward 25 centimeters.
Yes.
How did you come to this decision actually? Because like
it's easier. You have this more like a little bit. There's a metric, but then there's also this like discrete type of action space right now in here. Yeah, it's easier basically. Yeah. So yeah, this is finding the football, and then you can step on the stones and find the football. Basically that's it. So it works on a lot of environments. It is showing here, but let's skip that. And I like the part that because it's actually the exact same model, you can apply it back to do this question answering. So you take in a video, you ask the question, where does the trash can set? Is to the right of the toilet. And the wall is hanging on the wall between the toilet and the bathtub, so it's the toilet paper. So it's the exact same model that can do navigation, can also do this question answering. So it's more, the VLA is more close to VLM than VLA, basically. It's actually more like a general model that you can have knowledge about things, and then also you can output action. So that's actually what I hope the VLA is going into. So the reason why this is important is because eventually we also want this kind of reasoning ability for the vision language action model to have. It's not just doing like a fixed set of tasks. You should have some generalization ability to do reasoning and then extend to more complex scenarios. So that's why we have this framework in here. Last part is we want to apply the same thing to manipulation. So the same framework was ideally you should work in manipulation so that you have high-level policy to do where the hands are going, and then you have low-level policy to handle the grasping things. That was the hope. But then in terms of like giving a talk in here, I didn't make that deadline that way. So I make another deadline basically is try to have another framework that is close to what I described, that we still try to train the vision language action model on human data, but then have some way to transform the outputs of human action output to robot outputs. So this is the Eagle VLA paper. So what we did is we tried to train the vision language action model only on human data first. We train on egocentric videos. There's really, really very limited numbers of videos you can use. I mean, when we try to do this task, there's not a lot. So this listed out some example videos that have relatively reliable 3D annotations on the hands and any factor. So we use this video to do the training. I bring this up again because from this project, what we learned is really the difference between human action and the robot action is really just a transformation away, because you are transformation like this doing IK and retargeting, you can transform the human action to become the robot actions. So that makes me think, can we just train a human VLA and then go through some transformation, then it will become the robot VLA. So that's why we kind of start these projects on only training on human VLA. So this is a model that basically takes human videos, a few frames as input and language instruction, and then you want to predict a model hand, basically is a parameterized hand for human hands. So you predict the hand pose and also where the wrist is going to reach. And these models, which only outputs the human action, can actually be converted to robot action. So to do this, we create another teleop data set because we want to iterate very fast in manipulation. So keep using real data makes it very slow. So we have an iSet lab thing that we developed on our very similar teleop task we see in real, but now it's in sim. So we can iterate faster. So what we try to do in here is basically we find a mapping, a conversion between the human action and the robot action. So from robot response to human response, it's really a very simple 3D transformation because the mono response has its own coordinate system. So we need to convert that, the 3D locations of the robot hand wrist to the mono hand wrist. And then to convert robot fingers to human fingers, what we are doing is actually going for optimization process. The process is basically hoping the fingertip of the robot hand is going to align. So where the finger touch of the robot hand touch is exactly where the human hand finger is going to touch. So you align the fingertip, and then you do an optimization approach to basically to get the human hand pose parameter. So we basically figure out a mapping to convert the human video, the robot video, these robot actions into human actions. So once you have the human actions, you basically have the robot demonstrations, but you're actually getting human action out of it. And then you use these human actions to fine-tune this human VLA. So I'm keep basically training just the human VLA. There's no robot VLA here. So I'm even converting the robot actions to human actions. So we train a human VLA. The cool thing is that after you train a human VLA, that you can actually output the wrist pose and also the hand pose. So you can map it back into robot actions. For example, you can first map it to the wrist of the robot hand, and then also do IK to control other joint of the arms. And then you can also do retargeting to get the robot hand pose, so that you can convert the human hand action back to the robot hand. So I will show you some video, so for better illustration. So we have this task suite, we still keep developing, but different tasks. We also do demonstration collection in this task suite. But essentially, this is our human VLA output results. I'm also only visualizing the wrist, but we actually predict all the joints of the finger. And basically, the blue thing is the prediction, the red thing is the ground truth. So we are basically predicting 10 steps forward. So it's also action chunking, all the things are happening here. But the model is able to, given a few images, you predict where how the hand moves. And this basically converts to the same models after we fine-tuned on the robot here. It kind of converts to conduct the task in this similarly. So this is flipping it and then pulling the thing.
Question.
Yes?
What about the hand gestures?
Uh-huh.
If you adjust the trajectory of the hand, how do you predict the fingers?
So we are predicting the mono hand, so which means it actually has the parameterized hand pose and also shape. So it's actually 15 parameters, which is the PCA space of the mono hand. Once you predict the 15 parameters, you can obtain the hand pose and everything. So it's actually quite detailed human hand gesture predictions. It's not just wrist. Yeah.
Sure.
Yes.
So do you need to collect paired data in simulation and also like real-world human demonstration?
Not in this project. Not in this project. So this is more like a fine-tuning thing. It's not co-training. So it's okay. So we didn't. So the human data is really quite in the wild data. So that have relatively accurate 3D pose. The hope is that we still can fine-tune, have the robot data to fine-tune it, so that works. But I can show you the next slides that we do try to collect data in similar environments for both humans and robots. But currently for this very initial attempt, so we tried this. Yes. Right. So again, this is the simulation is really for evaluation purpose or studying the algorithm purposes. We're not counting that this will be useful for sim-to-real. It's really just for us to develop the methods and then fast evaluations on the methods that try to do this cross-human and robot embodiment kind of learning. Yeah, so this is something I mentioned that earlier that I just want to answer your question. So we also try to make this work, but it doesn't make in time to CVPR. The paper is 6 pages long already, but we didn't eventually make all the task work, so we didn't submit. But we are also having some efforts. Basically, you collect real robot data, and on the site, you can collect real human data. And this is using Vision Pro. So if you have enterprise license from somewhere, then you can have main camera access. So you can actually record the human videos, and then you can also have relatively accurate hand pose estimation for this video. We record it, so you can collect human data doing the same thing. So we are exploring the similar framework, but using real human data and real robot data to do it. So that's the thing. But that is, again, teleoperation is one way. I'm going to end my talk. But basically, we are also still exploring sim-to-real. So this is some grasping thing we are doing, that we are exploring Dexter's grasping, but in simulation and do sim-to-real. So I do feel like sim-to-real might still worth to basically explore, but on the purpose of just very low-level contact interaction instead of very complex thing using digital twin and things. So I think for the final milestone of contact and grasping, there's possibility that use this sim-to-real on here as well. So that's all. So I think in general, so what is the thing I try to convince you is basically, so you can have controller, you can have teleop, you can have sim-to-real, but it's not going to, I don't believe it will work in task level. I think it would be very useful, and then with limited data that solve a lot of problems in low level in contact, for context. But it's still very hard to get large amount of data to do more planning or more complex things. So I do believe in that we should leverage a lot human data at the same time that we train not just VLA for particular robot, but maybe agent agnostic or people say cross embodiment. But I want to emphasize more on the human part that we can train human VLA. And then connect these two. So this is more like the path I believe in now. So that's all. Thank you. Let me know if you want to.
We have 5 minutes for questions.
Yes?
So for an active sensing task, can packing task,
right.
Will the robot actively search for the can if the can is not?
No. So the training data is too small now. So it's not doing that intelligent actions. So it's more kind of fixed action. So it's always left and right, left and right. Yeah. It's not that. But I do believe in if you have given enough data that see around, it can emerge this kind of behavior. But yeah, we're only training on 50 or 100 demonstrations. So it's not that intellectually searching for things. Yeah.
For the robotic teleoperation, the camera seems like a shake a little bit.
Yeah.
How would you learn from technical policy?
Yeah, we are fixing that. So I mean, the body will always shake. So some stabilizations of vision might be needed. But also in the leg, we are improving the design of the leg a little bit on the hardware wise, so to stabilize it. Yeah, so that is just something we're working on.
For the open VOE training with human video, egocentric video, do you think the camera pose could also be useful as part of the action space?
Yeah, I think we do. Oh, the camera pose. I don't think we have explored that yet. But yeah, so The thing is just it's very noisy. It's just the
human video will always
yeah. So in that case we are actually putting things in the camera frame now. So for the action model, so it's actually in the camera coordinate space. So we are not in the robot frame or the world coordinates. So the action is following the camera more like that now. Yeah, I think it's just from those videos you don't have very accurate camera models. Yeah, so I think that's also something we are missing. So when we are collecting new egocentric videos, we should also get the accurate camera model. Yeah.
Human video with robot calibration.
Yes, you can get it. Yes. Yes. Okay. Any questions?
I have a few questions
Okay.
from online audience. So one question is, how would you compare X42 with H2O?
X42 with H2O. Oh yeah. So that's the big things that actually H2O. So this is a comparisons in here. So I think the two method highlight to 1 and 2 actually makes a difference. So for example, H2O is actually using this one. So the global tracking is checking the absolute positions of the point, the key points, and we are doing a velocity tracking plus local relative pose tracking. So that is one difference. Second difference is really a lot study on data side. So I think H2O only use the whole data set, but we do a lot of study on which data, how data affected. We were trying to tell a story on curriculum learning in the beginning, but again, one student figured out a way to create a very, very good data set, so stopped us to tell the story. So I think there must be a way to filter and automate this data curation process. Maybe if that student is not there, that would be a good story. But yeah, so manually filtering is still good, but we will find some way to automate it and then also enlarge the whole data set. Yeah. So these 1 and 2 are the major differences. Yeah. It's not that good, but it's important. It's very, very critical to make this work. Okay. All right.
We have one more question.
Okay.
Okay.
Yes.
So in terms of the size of the VLA models that are sort of useful and what hardware they can run on, so I think in your cases you're running in the cloud. Was that thing?
Yeah, it's running on desktop actually. You're sending the picture back to my desktop and then run it there and then send it back. So I think we are using actually a small 1.5B language model. It's not very large, and then the frame input is actually 8 frames as a history. So we try to use something called long VLA before, which is the new VLA versions that have 128 frames. So that is not working because one inference takes 4 seconds. So that's even on the GPUs on the desktop. So that's impossible. But these models, and then after some quantizations, we are able to run it maybe half a second. That is the maximum speed. And then there's some transferring pictures or some latency there. So I think we hope to, as also for NVIDIA itself, yeah.
They'd like to support this on RN or something
Right.
If they could, right?
Yeah. Well, I'm directly working on the team that do this quantization and VLA efficiency, but it's still, it's not a very easy problem to directly work on.
You go to smaller fine-tuned models that they're losing some other capabilities.
So I think the task we are doing actually is not that difficult now. So it's not that big difference, especially when we actually try to show, initially I also want to tell a story that long VLA, a long context VLM model will be much more helpful. When reality is not. So the vision language navigation problem is kind of not very well defined in the current setting. Actually, a short history works well. So I think there will be a problem that requires long context, but right now it's not that necessary to have bigger model, a longer context model. Yeah. Thank you.